Hi everyone and welcome to my YouTube channel. So we're continuing our inequalities playlist, and after we've discussed in the first lesson the AMGM, the introduction to AMGM, we learned what is the statement of the general AMGM. Now of course we'll be moving to the practical side by solving simply practical examples. So probably we'll be discussing AMGM in the next 3 videos. And each video will be discussing a group of ideas, and for each idea we'll be presenting some nice examples. Alright, so this is our first starting examples on the AMGM, so things are a bit easy today, but of course we'll be leveling up the difficulty in next videos. Alright my friends, so what are we waiting for? Let's get started. Alright, so our first example is the following. So we've got a sequence A1, A2 till AN in numbers, and they are positive numbers. So like let's say all of them are greater than 0, and we've got the following condition. So we know that A1, A2 up to AN is 1. The product is 1. Okay, that's nice. So what is the thing that we need to prove? We need to prove the following inequality. 1 plus A1 times 1 plus A2 and so on times 1 plus AN is greater than or equal to 2 to the n. Alright. So we have a set of n, we've got n numbers, they're positive, their product is 1, and we need to prove some inequality. So first of all, you notice that we have a condition on the numbers. Basically, inequalities that will appear usually, you can divide them into 2 sets. The first set is inequalities that don't have any condition. For example, some inequalities are always true. Let's say just the AMGM, for example, we did not have any condition on these, right? Beside that, they are, for example, positive maybe, or even sometimes they don't even have to be positive, like this inequality. Okay, or other inequalities have some condition, like this one, for example. They are telling you that the product of the numbers is 1. Of course, that in itself changes the equality cases, because here, for example, the equality case is when x is equal to y. But here, when is the equality case, if you try to think about it? Okay, the most logical thing is to think when all the numbers are equal. But actually, if all the numbers are equal, this is not equal to 2 to the n. We need to have some other condition. Of course, here, from the condition, if all the numbers are equal, that means all of them are equal to 1. So, if all the numbers are 1, then indeed, you will see that this is 2, this is 2, this is 2. So all of the numbers are 2's, and hence the equality holds. Okay, so basically, as you can see, the condition here kind of lets us easily find the equality case most of the times. The product of numbers is 1, all of them are 1 here. Okay, so now how can we proceed with this question? Of course, now the only tool that we have in our pocket is the AMGM. So let's see how we can do that actually here. So if you take a look at this inequality, you see that this is the bigger side, the LHS, this is the smaller side. So if you just want to apply the AMGM, we need to have, remember, a sum. Like a sum of numbers, we apply the AMGM on them to make them a product. Well, take a look here. Do we have a sum? No, right? This is in fact very bad for the AMGM, because in the AMGM we know that the pi, or the product, is less than the sum. So things actually are bad for us here, because we have a pi here. In fact, we can say that this is less than something with the AMGM. Okay, so what can we do? Are we screwed? Well, actually, no. There is actually some sum here, but it's not kind of external like if you want to apply the AMGM externally, you can't because you don't have like a sum here. For example, if these were sum, okay, that's good. Okay, so what are we doing then? No problem. We'll be applying the AMGM internally, not externally. For example, look here. You do have a sum, right? You have two numbers. Remember the AMGM, like x plus y is greater than 2 root xy. So why don't we do the same thing here? So let's try to do that. What happens? If we say 1 plus a1 is greater than or equal to 2 root, of course, it's just a1 because the other number is 1. Okay, of course, we'll be doing the same for the other ones. In fact, like from the beginning, always, well, once you write one inequality, then just like here, for example, what do we want to do? Just take the pi, right? Pi of both sides. So that means the pi of 1 plus a1, or like just ai actually, but no problems, like we're not here formally writing everything. So if I wrote something like this, then please accept it, okay? So here we also having pi 2 root a1. Okay, this is the LHS. Perfect. But the RHS, is it cool? Like, is it what we want? Let's see. So first of all, we've got pi of 2 times something. So we've got many 2's. How many 2's? 2 to the n. Okay, perfect. We've got what we want here. So actually, this is 2 to the n times the pi of root a1. But guess what? Root a1, what is the pi of root a1? This is just like the square root of the pi of the a1, or like all the numbers. But guess what? We already know that the product of the numbers is 1. And hence, actually, this is nothing but 2 to the n. And that finished the question. Alright, so as we saw here, instead of, like we can't apply AMGM like kind of externally on all the numbers. So instead we simply applied it internally on each bracket. And of course, maybe sometimes like the 2 might help you here. Like how can 2 come from AMGM? If you just applied it on 2 numbers, right? And also if you think about the equality case, then it also makes sense, because the equality case is when all the numbers are equal and they're all equal to 1. So here when you apply the AMGM here, then the equality case holds when a1 equals 1. And that makes sense because this is indeed the equality case. Okay, so that was our first example. As you can see, it was not difficult at all. We just applied the AMGM on each bracket, and the condition was handled smoothly. The product, we got it's 1. All right, let's move on to the next example. Okay, now we've got 3 numbers that are non-negative, and they're telling us prove the following inequality. So here we don't have a condition. A plus b times b plus c times c plus a greater than or equal to 8abc. Okay, let's see how we can do that. First of all, I really want you to think about this yourself. You should be able to solve it. Alright, so now the idea of this question is exactly the same as the previous one, because if you look at it, we also here have a product. We can't apply the AMGM like externally. So what happens if we just do it internally? A plus b and b plus c and c plus a. Let's see. A plus b is greater than or equal to 2 root ab. So now by taking the pi of a plus b is greater than or equal to the pi of 2 root ab, which is equal to 2 times 2 times 2, it's 8, and root ab times root bc times root ca is just abc. And hence we're done. That's it. Of course, here the equality holds when here like all the equalities hold, and that happens of course when a equals to b equals to c from the AMGM equality case. Okay, so as you can see, this is just the same as the previous example, but there we had 1 here and we had some condition. Here we don't have such a thing. Of course, here if they told you the condition ABC is equals to 1, then that will just become 8. All right. Actually, there is another way to solve this. Of course, this is the easiest way to solve it, but there is actually another way. So let's say maybe you're solving this question and you thought about expanding because you were thinking like that. In the AMGM, I need to have a sum, right? Here I have a product. So basically, how can I get a sum? By expanding, right? If I expanded everything, I would get a sum. So your plan is simple. I'm going to expand and then try to apply AMGM. Let's see what happens. And another thing I want you to kind of master is the expanding. You need to learn how to expand in a nice way, or like in a fast way and a simple way, because you don't want to waste time expanding. Just like some beginners expanding, they will like do something like this. Okay, let's try it here. How do we expand? Okay, let's say like here, solution 2. So I don't want you to expand like this. A, and do it like this, A, B, then C. You write it, and then saying A, B, then A. So it's A square B. And then, like, okay, we're done with the B. We go to the C, and this, and then this, and so on. Like, you'll spend forever if you apply this strategy. Instead, you should be expanding in a really clever way. How exactly? What do I mean by that? Okay, let's see. So basically, we want to expand by of A plus B. It's totally okay to write like the numbers. For example, you can do actually say A plus B and B plus C and C plus A. If you once you become an expert, you don't even you'll just be using the pi A plus B, and you can kind of expand it in your head even. So let's think what will happen when I expand this. So the first thing you should know is how many terms are you expecting to get? How many terms will I get if I expand all of that? If you think about it, just using some combinatorics, some counting, like really simple counting, here I have 2 terms. So 2, here 2, here 2. So if I expanded that, I will be getting 2 times 2 times 2, which is 8. So I'll be expecting 8 terms. Perfect. So we're expecting to have 8 terms. So if we received less than 8 terms, then we are doing a mistake. Okay, what is the next thing we'll be doing? The next idea actually, is this symmetric? Is this expression symmetric? Most of the times what you're expanding is symmetric. Most of the times. Of course, sometimes no, it's not. But here it's symmetric. So what does that mean? That simply means that when you multiply, when you expand, you will not expect to get something like this. A square B, for example, plus like some stuff. But we don't have A square C. This is not symmetric because, as if you remember, we said that a cyclic, the difference between cyclic sum and symmetric sum in the previous lesson. We explained that. We said that if we have a sigma symmetric A square B, then this will include A square B and A square C. So you see, from here, this product, we're looking at it, we're saying, wait a minute, this is symmetric. So I should be getting a symmetric. So once I get A square B, I will immediately know that actually I do have a symmetric A square B. And of course, this saves tons of time. So let's see actually in our example here. Let's see first of all. If you just take some random, okay, here, take a look at it. A, B, and C. Okay, so actually I'll be getting some A, B, C. Okay, that's good. That's one term. ABC in itself is symmetric because it's already ABC. How many ABCs will I get? Think about it. Of course, you need to be using some counting here. How many ABC do we have? Can we get from this? Well, the answer is 2. Just 2 ABC. You can think about it. Here, if I started with A here, then here I can't use the A, so I need to use the C. And here I'll have to use the B. So it's the first ABC. Otherwise, I'll be using the B here. So I must use this C. So I must use this A. So it's just 2 ABC. All right, perfect. 2 ABC. So now I just have 6 remaining terms. Okay, let's see also something random. So if I put an a here and let's say an a here and some maybe like a b here, so what will I get? I will get a square b. Think about it. This is a square b. Remember, everything should be symmetric because the whole thing here is symmetric. By the way, like try to think about it if you don't believe it, because if you have a symmetric thing, like a symmetric stuff, or like let's say, okay, here you have pi, a symmetric pi, right? Product, because a plus b and you've got b plus c and c plus a. Once you expand it, everything should be symmetric. Like you don't really need to kind of think about it mathematically, just using logical. So here, once we got a square b, we already know that we must get a sigma symmetric of that. And guess what? How many terms are there in a sigma symmetric a square b? Think about it. What did we say in the previous lesson? When you have 3 variables and you go over a sigma symmetric, you always have n factorial. So here 3 factorial, so 6. So perfect, we've got 6 here and we've got 2 here, so indeed we've got 8. So we're done. This is how we expand in a really fast way. Of course, right now, because we're explaining it, it's taking like too much time, but like if you just master this, you'll immediately say pi a plus b. You already like know that you'll get a and some number, a b for example. So we must have a sigma symmetric a square b. This already kills 6 of these. The remaining are what? If I take a b c and another like b c a, so we're done. That's the product. Oh, sorry, that's the expanding. Okay, so now we expanded that. What next? Of course, the question asked us to show this is greater than 8 abc. Perfect. So I need to use prove that this is greater than 8 abc. So I already can cancel 2 abc from here and there. So actually, I just need to prove that sigma symmetric a square b is greater than 6 abc. Now I do have a sigma, so I simply can apply the AMGM. And if you apply the AMGM, you'll be done at once. You can just think about it. You have how many terms? 6. So if you apply the AMGM, it will be 6 here and the 6th root here. And just take, because this is symmetric easily, just let's focus on a. What is the power of a? Okay, we will be getting from a square b a 2, from a square c another 2, so that's 4, and from ab squared and ac squared we'll also be getting 1 and 1, so in total it's 6. So that means we can delete all of that, they will cancel, and we get abc, and we are done. So as you can see, this is just another solution using expanding. Of course, you should go for the first solution because it's much easier here and more direct. But just showing you that expanding, like usually, is always one way to solve the questions that use the AMGM. This is kind of a classical thing in the AMGM lesson, that you simply expand, cancel stuff, simplify, and then apply the AMGM. Alright, so that was our second example. Now we can move to the third example. So now, let's say we also have 3 numbers. They are positive. We need to prove that a cube over bc plus b cube over ca plus c cube over ab is greater than or equal to a plus b plus c. Alright, so let's focus here. What can we do? As you can see, we've got some fractions here. So how are we dealing with fractions? We've got a cube over bc, b cube over ca, and c cube over ab. Of course, this is nice, a plus b plus c. Okay, so here usually when you have fractions, you have 2 ways to deal with it, especially when you have simple fractions, like not something like a cube over, let's say, b to the 4 plus c square plus a. This is something complicated. But here it's really like easy, just bc, ca, ab. So one idea to apply here is simply to go for like clearing denominators. And this is really easy if you multiply both sides by abc. So let's go for that. So if you multiply both sides by abc, Of course, this is solution 1. We'll be also introducing another solution. But if you multiply everything by ABC, you will just get a to the 4 plus b to the 4 plus c to the 4 is greater than or equal to ABC times sigma a. Okay, of course, like ABC sigma a, we can expand this as well. So we can just write it as sigma a square BC. Okay, or of course you can like write it as a square BC plus b square like AB square C plus AB C square. Okay, so now what? Now, okay, here we've got a sigma and here we've got a sigma. How can we solve this question using the AMGM? If you remember, we solved in the previous lesson. We basically solved a similar question, which was show that sigma a square is greater than or equal to sigma AB. So if you remember the idea, we simply said, okay, I'm going to catch a single AP here and try to pair it with some of the guys here. So for example, it was very easy because a square plus b square were able to like get rid of this. So now we'll be doing a similar discussion, and this is really important idea you need to master in the AMGM because it will appear a lot. So let's catch one of them. Let's say a square BC, and we'll try to get it from these like guys. So how can we do that? Of course, we'll be needing an A and a B and a C, so we'll need at least like all of them. Of course, that's not enough because if we apply the AMGM here, it will be kind of garbage, right? You will get like 3 and then a cubic root of a to the 4, which is not what we want. Simply looking at this, you can see a single C, a single B, but 2 A's. So that just simply suggests that we add another A. Now if you thought about it, it's like now super clean, and in fact it gives you exactly that times 4. So now that's perfect. So now if we put that as 4, now we're done. Always once you reach one of them, like once you find one pairing, then you're done. Now you'll simply like take like you can either, as we said, either apply similarly for the others, for like a b square c and a b c square, and write them and sum them up, or like even shorter, because we're pros, we know how to use sigmas. We just take the sigma of both sides. Of course, here then you will get a 4 here and a 4 here, and they will cancel, and we'll be done. We will get this. All right, so that's basically the first solution, which is just expanding. We expanded everything. We multiplied basically by ABC, cleared the denominators, and then we got this idea, and we used the pairing technique. Always keep that in mind. The pairing technique is really powerful. The pairing. It's not like just pairs, but even like more. Like if you just combine some stuff here to beat one guy here on the RHS. Usually, most of the times, by the way, the thing you take is from the lower hand side. Like here, for example, A is in this like less than or equal to side, and you try to grab some guys from here. Sometimes, however, maybe you like the same idea but for reverse. Maybe we catch one of them and we take some of these to beat it. All right, so that really depends on the question, but most of the times you will see it like this. Another solution is even without expanding, without clearing the denominator, you can actually solve it immediately by using the pairing directly. So now instead of like working on this, we'll be working immediately on that. So we'll just be working on the A, like let's say we want to have an A here, and we need to think, how can we get an A from these guys? Of course, like right now we've already spoiled it because it will follow the same sequence. You will get like 2 of the first and one from the second and one from the third. But if you just were thinking about it logically, you can immediately guess that as well. For example, let's see why this is logical. So we want to get an A, right? So the only way to get an A in the numerator is to use this These are bad. These are like in the denominator. Okay, but once we got A, then we got B and C here. So we want to get rid of them. The only way to get rid of the B and C in the denominator is to use these, because this one gives you a B in the numerator, and this one gives you a C in the denominator. So we need to actually use all of them. But again, this is not enough, because if you use like just these, that's not enough. Like the B and C are not completely cancelled. We got a B here and a B here, alright, but here we've got B cubed. So we still need another thing to cancel a B from here and a C from here, and hence we need to use double of that. And of course that just gives you what we wanted. So we can simply write the following inequality: A cubed over BC plus A cubed over BC plus B cubed over CA plus C cubed over AB, and this is by AMGM. By the way, it's very important that when you write a formula solution, you either specify here, you say by AMGM when you want to write an inequality, or you can write the AMGM here, like the inequality you're applying under the thing here, like the inequality sign. I prefer in a formula solution to write it here clearly, but that like works as well. Okay, and of course then similarly, sorry, here of course we've got 4. Then similarly we get the others, and we're done. We get a sigma and we're done. Alright, so that was also a nice example, because we are learning in it like the pairing technique, and as we said, this is a really important technique. Okay, the final example for today is the following. Okay, these are positive numbers, and we need to prove the following inequality. So I'll be writing this as a sigma, because I'm too lazy to write all of them. And here another sigma. It's AB times root A over B, B plus C, and C plus A. Alright, hold on a second. This is too ugly, right? Okay, this is like manageable to deal with. Sigma AB times A plus B. But this is, come on, it's a bit scary, right? You've got AB and a big root, and you've got A over B and lots of stuff here. Okay, let's see. We'll try to break this one logically, step by step. So let's, of course, we don't have any condition here. We're just looking at this question, and we need to work with it. Okay, so how can we use the AMGM to like reach from here to there? One idea that you might think of is to use kind of the pairing technique. So we catch one of these and try to get it from the combinations that we have here: AB and A plus B, BC and C plus A, and you know the other ones as well. But if you think about it and try with it, you will simply by the way, like before we even like bother working with this, clearly here like we've got some garbage stuff, right? Like we've got A over B here and AB here. So let's like try to simplify that. So basically the RHS is actually, they just like want to make stuff kind of pretty. They're putting that, but we don't need to even care about that. We can just put the AB inside by making it A squared B squared and putting it inside and cancel. We will simply get that we just need to actually work with A cubed B and B plus C and C plus A. Alright, this is like more real. We don't need to bother working with that and that. We got rid of the fraction even. Okay, so so this is what we need to work with. So okay, let's use that idea that might come to your mind. We want to have a B plus C and a C plus A. So wait a minute, I should not use this. I should use the other guys, which are BC and B plus C, then CA and C plus A. By the way, when you are applying the AMGM, especially like in this lesson, the AMGM, okay, no worries. You can write these like this, write all the terms, because you need to actually know how to apply the AMGM on them. However, in later lessons, most of the times we'll be just working with sigmas, so don't worry about it right now. Because we want to kind of use the pairing technique, we always kind of don't work with the sigma in the AMGM. All right, let's take a look at it. We've got a C plus A, B plus C. This is the perfect what we need. But guess what? This is not working because we got a C. We don't want to have a C here. So unfortunately, this idea is bad. Doesn't work. So we need to come up with another idea. We can't just apply the other ones. So the pairing technique is kind of not cool here. So what can we do instead? Okay, so now let's look at the question. You can see that the LHS is really super nice. It's not complicated. It's simply sigma AB times A plus B. But the main deal is here. This is the real deal, the problem. Because we've got a root and like A cube B, this is really not fun at all. So instead of going from the LHS to the RHS, like this, as usual, from the AMGM we always go like this, we'll be doing the opposite. We could be going from the RHS to LHS. So we want to apply the AMGM, but in reverse. We will be starting with the lower hand side and hoping to get the LHS. Okay, so let's, like with that in our mind, we will be just picking one of these. And our goal is to apply the AMGM to get like some of the LHS. Okay, so let's see how can we apply the AMGM here. First of all, some nice thing is that, remember the AMGM, when you apply it on two numbers, it gives you a square root. So this is an indicator that we probably should use two numbers, like a number here and a number here. And then like we want to get, okay, we will get a square root and we will get these guys here. So now like our job is really simple. We just need to partition these guys here into stuff here and stuff here in order to get something beneficial. So how can we do that? Well, if you want to split these guys, then there are lots and lots of ways. For example, you can just put a single A here and A square B and all the others here. Like this is one suitable way, for example. There's also like A square or like AB and tons of them. Should we really try all of them? Or there's perhaps some technique or some guidance, something that guides us to avoid the bad AMGM application and to guide us to apply the correct AMGM? Well, of course there is. What is it exactly? The idea is basically to use the equality case. If you remember, I told you when we discussed the AMGM, we said that the equality case holds when all the numbers are equal. So here, if you want to respect the equality case, let's first of all look at the original inequality. When does the equality hold in our original inequality? Luckily, we don't have any condition. So most of the times it's when all the numbers are equal. And we can easily check it. If the numbers are equal, then this is 1. You got A squared here. And this one is 2A, 2A. So it's 4A squared. So it's times 2A. So it's actually 2A cubed. And the sum of them is just 6A cubed. And here what do we have? We have A squared times 2A. So it's 2A cubed. And also, like, if you add them up, you get 6A cubed. And that's it. So the equality holds in our inequality when all the numbers are equal. So that means we need to respect that. So for example, now is this a suitable thing to do? And stuff? Sure no. Because like the equality here in this AMGM holds when this is equal to these. Clearly, like, we don't want A to be equal to all of that. So, okay, now we have some really strong guidance. Because now we know that, for example, if we have B plus C here, then C plus A can't go here. because now nothing will beat it from here. So it must be here. Okay, that's super nice. So now we have b plus c here and c plus a here. And by the way, these are equal in the equality case. So now we need to partition the a cubed times b into stuff here and here. Okay, also by respecting the equality case, we have actually only two possibilities now, which are the following. Either we have an a square here and an ab, or the opposite. We have an ab here and have an a square here. So okay, instead of like dealing with tons of possibilities, now we reduce it because of the equality case into only two. That's why I really want to stress the importance of the equality case, especially in the AMGM lesson. In other lessons, sometimes it's like the power of it. For example, in Cauchy, once we discuss Cauchy, you'll see it's unfortunately not that important there. But here it's really important in the AMGM, because the AMGM holds when the two numbers are equal. Okay, so now which one should we pick? The first or second? Well, of course, we just have two possibilities. We can try both. By the way, like, of course, we should have here 2, or like divide this by 2. But this is just a secondary thing. Let's try to think which one is more suitable. So let's look at our original inequality. All right, we are simplifying the LHS, sorry, the RHS. We want to get rid to reach the LHS. So if we apply the second one here, the second one, what do we get? If we expand this, we get AB squared. That's nice. I will also get here AB squared. I will also get an ABC. Well, here I don't get an ABC. But what happens here? If I expand this, okay, a square c. Actually, I will also get an a square c here eventually. But here, if I expand this, I will get a cube. Well, here I don't have a cube. All right, so now I got two stuff that I don't have here. I got a cube, sigma a cube, and a sigma ABC, or 3ABC. Here, however, if you think about it, I'll be having a square b and a square c. both are here. I will also have like a square b is also there, but ABC is not there. So guess what? If I like apply this or this, here this one will give me two different stuff, this and this, while this will only gives me this like different thing. So probably, logically speaking, I should pick this, like the first application. Another reason why we should avoid the second one is something, if you're still a beginner in inequalities, you will not really appreciate, but sooner, once you get more expertise here, it will be really clear that the second one is bad. The actual reason is that sigma a cube is really a big thing. Sigma a cube is too big. It can't be beaten by these guys here. However, ABC is really a small thing, because you can think about it using the AMGM. Usually, most of the times, always when you apply the AMGM on a symmetric stuff, you will get ABC here, right? ABC like maybe something like this, but always ABC is on the smaller side. So let's say you got something like this. Then you have this actually. So as you can see, ABC is always too small. So this doesn't matter, because if we went from the RHS to that, and then we want to prove that this is greater than that, then it's already, we know that ABC is too small, so it doesn't matter. However, sigma a cube is not the case. In fact, sigma a cube is greater than anything. It's in fact greater than sigma a square b, it's greater than sigma ab squared, and lots of other stuff. We will be actually, you will understand that more during the next lessons, especially once we discuss Muirhead's inequality. So don't worry about it right now, but this is just, I'm telling you why probably we should pick the first one. All right, so let's do that. Let's go ahead and pick the first one. So now, by simply applying this inequality, C plus A, AB, of course AMGM, it will simply gives you 2 of that. And then of course you'll take the sigma of both, sides, and you'll simply get that the RHS is less than, okay, let's move the two here, or you know what, let's multiply both sides by 2 here, and then like just cancel. So now we just need to prove that 2 sigma AB, A plus B, is greater than the sigma of B plus C, A square, plus the sigma of C plus A times AB. Okay, let's expand and cancel stuff. So by expanding now, we simply, the LHS here, by the way, we need to prove this. I always like to put a question mark when I need to prove something, because if I can't prove it, then I'm done. But it's wrong to say it's equivalent, because this is not equivalent to the original question. Be careful of that mistake. This is not equivalent to this, because here you applied one inequality. You can say actually it is enough to show this. It's enough. Once we show it, we're done. But this is not equivalent to the original question. Okay, let's not care on that. This we care about it after we find the solution, a working solution, in order to write it formally. So basically, now the LHS, if we expand it, it's easy. It's simply 2 and A square B. So 2, this, that. Here, however, we have A square B, and we have A square C, and okay, ABC, sigma ABC is just 3 ABC, and sigma A square B. Okay, let's cancel the stuff that we can do. Once sigma A square B with the 2 here, we also have sigma A square C. We can cancel it with the 2 here, because by the way, you can check that sigma AB square is the same as sigma A square C. They are just the same. And sigma A square B with the whole sigma A square B. Alright, so now we just need to show that sigma AB square is greater than or equal to 3ABC. But guess what? This is just correct from the AMGM on 3 numbers. And yes, that's it. We're done. Alright, so a quick review for this question. First of all, we said that using the AMGM classically from the LHS to RHS is really does not work here. The pairing technique doesn't work. Instead, we said, wait a minute. First of all, let me write this in a clean way. That's it. Then we said, probably I should go from the RHS to LHS. And probably I need to apply AMGM. And because I have just a square root, I should probably apply the AMGM for 2 numbers. Then I had tons of possibilities, but using the equality case, I really had only 2 possibilities. We excluded one of them because of the sigma A cube. So we said probably we should apply this, and indeed we just applied it and cancelled, and we just got the simple AMGM. And we're done. Alright, so as a summary, today we solved some examples and we learned some ideas. First of all, the first idea in the first question, we saw here how to apply the AMGM, not externally because we can't do that, but internally on each bracket. And it's really cool idea since the product will just cancel, it will become 1. Here also we solved it using the same idea exactly, apply the internally AMGM here on each bracket. We also solved it in another way, which is the expanding and then pairing way, like we expanded and cancelled stuff, and we simply got it using the AMGM from here. Okay, also we learned about the pairing technique. We said that we have 2 possibilities here, either to clear the denominators or even without clearing the denominators. Both work by just applying the pairing technique. Whether you want to you just say, how can I get an A here using these guys here? You just need to decide logically. So we did that here. And we saw that this is the logical combination. Once you get one logical combination, then you're done. You just say like we take sigma and divide by 4. Same thing here. Finally, we ended our lesson with the final example. which is simply kind of scary because of its ugly form here. But really, using logical thinking, it was not scary at all. We just said we need to apply the AMGM in reverse, and because of the square root, we need to apply it on two numbers. And because of the equality case, we have only two possibilities. One of them we probably said it's bad idea, so we just applied the first one and we got it right easily because everything cancelled, and we got it using the AMGM. Alright, my friends, so that's it for our first starting examples on the AMGM. In the following lesson, we'll be also discussing another set of ideas and some nice examples also on the AMGM, because we want to master the AMGM before we can go further with any other inequality, as this is really an essential one you need to master in your mathematical inequalities journey. Alright, my friends, so I hope you enjoyed this video. Please like, share, and subscribe to the channel, and see you guys in the next video.